Today we're going to talk about reinforcement learning. This refers to a handout I've uploaded to Blackboard with the same title, Reinforcement Learning. It's a copy of Chapter 13 out of a textbook on machine learning. Reinforcement learning is based on adaptive critics and approximate dynamic programming. Both are methods that allow learning of optimal control strategies inside an environment without specifically setting up an optimal control problem. It's fundamentally a method for an autonomous agent to learn a control strategy and to choose optimal actions. So if we have an autonomous agent, which really means some kind of device that we're trying to control, we want to choose optimal actions to achieve goals. So an example that's easy to understand is a mobile robot. Let's say that you have a robot in the room. Imagine our classroom. The robot starts in front of the classroom and it wants to go out the door. So it starts taking small steps, small movements throughout the room. And as it does this, it collects rewards along the way. And once it gets out the door, it gets a really big reward for achieving the goal. And this is a method to use that reward structure and those motions, which are really the robot exploring the space, for it to learn how to get out the door in the fastest or most optimal manner. Obviously, it applies to manufacturing, where you try to minimize cost and maximize output. And then an example we'll look at later on is backgammon. This was really successfully applied to playing board games. So the idea is that an agent performs actions in an environment. So the actions are essentially the control policy. The environment gives it the rewards, and we want to maximize that reward, or you can look at it as a penalty function if you invert it. One of the things we'll talk about, not in this lecture, but the next lecture, is cue learning. And it's a way to learn from those actions and rewards to acquire an optimal control strategy. And the key feature here is that you get delayed rewards. So for example, the robot that's trying to get out of the room, that reward of getting out the door will be delayed multiple steps as it moves around the room. So this cue learning allows that reward that's happening 10, 15 steps ahead to get propagated back to the initial position so that it knows what the best way to go is from that initial starting position. And this is true if the agent has no prior knowledge of the effects of its actions in the environment. So it just moves, has no idea what's going to happen, but then the environment gives it a reward. So cue learning is related to dynamic programming, which is a different field of computer science, but it's a method to solve optimization problems. All right, so we'll have to define some terminology here, and I'll draw some block diagrams and relate the terminology to control systems that we already know. But the key feature here is that the goals have to be expressed as a reward function. Doing a good job with creating these rewards is key to getting this thing to work. So really what it's doing is assigning a number, a numeric value, or a payoff to each action. And so that's how it figures out, well, is this a good action or not? And that's the reinforcement. Bad actions are not reinforced, good actions are. Examples, like I've been talking about a mobile robot. It travels, the reward is it travels from A to B in maybe the shortest time or the least number of steps. Manufacturing, the reward would be the value of the goods minus maybe the cost to produce. So in a sense, the net profit. Taxis in a city, so you'd have the reward attached to fuel costs and maybe the wait time of the passengers. So the key, again, to all of this is making the reward structure work. By the way, we're going to go through a lot of just theory and definitions. You'll really see how this works in the lecture that follows this, where I do a really simple example of an agent in a grid world. we'll calculate values and go through the example. But here's a good picture of what's going on. We have the environment here, and then we have an agent. And the agent is in an environment, and so it gets its state from the environment, maybe via sensors or other information. So that you can think of the environment as giving the agent its state, because the agent is in the environment. The agent says, okay, I'm going to take this action, which then goes to the environment because the action gets the robot or the agent to a different place. And then the environment gives the agent a reward based on where it was and what it did. So this is terminology for reinforcement learning here, and then control theory terminology is here. So S is a state vector, and that's exactly the X or state vector in control theory. In reinforcement learning, we say A is an action vector. So that's just like the input to the system, U. And then the reward value, R, mapped to control theory, is the inverse of the cost function, J. So looking at the picture here, the agent starts out at some initial state in the environment. It decides on an action, and the environment gives it a reward. So state S0, A0, reward R0, and then the environment gives it a new state. So the action in the environment, you end up in a new state, and then you repeat. The agent chooses an action, receives a reward, ends up in a new state. Keeps going forward, dot, dot, dot. So the goal is to maximize the total discounted future reward. That's the reward that it's going to get going all the way to the door or not going to the door. If you're doing this in terms of the cost function, that would be maximizing 1 over the cost function from the initial time all the way to the final time. So we have to define this discounted total reward. And if we're starting at state S0, so each state is going to have this discounted total reward, and we're going to define it to be a V. So V is defined to be the discounted total reward. So V at state S0 is the reward it gets for taking an action, plus the reward it gets going from state S1 to S2, the reward going further, the reward going further, and it's discounted by this discount rate, gamma. And gamma is going to be less than 1, so the system collects an immediate reward. It gets discounted by the fraction. So let's say gamma is 0.5. So then the reward at the next step is 50%. And then the reward of the following step, 2 steps ahead, is going to be 0.5 squared or 0.25, right? So the rewards in the future get discounted. So gamma controls the emphasis on the immediate reward. If gamma is 0, no future rewards are considered. If gamma is equal to 1, then all rewards in the future have the same weight. All right, so we have our rewards function, discounted reward V, that we're going to use to evaluate policies. Now we need to define exactly how we make a control policy. So a control policy is defined to be this pi function. Pi maps a state to an action. So it's really a controller. So we're at a given state S. This controller, or pi, says, okay, if I'm in state S, I'm going to do action A. So if we're in state S0, pi says, I'm going to do action A0. Okay, so that's pretty straightforward. An example of this that I've been talking about and we'll keep looking at is a guy named Tesaro in 1995. Made a program called TD Gammon. This plays backgammon, and in 1.5 million games played, it became a world-class backgammon player. So this thing started out learning how to play backgammon against some computer backgammon players, and then it played people, and then this program actually got entered into tournaments to play professional backgammon players, and it worked its way up, kept learning and learning till it became a world-class backgammon player. All right, so one question is, well, how do you create this pi policy? This is a controller. How do we get it? What do we do with it? How do we arrive at it? One way is to make pi a neural network, which fits in with what we've been doing in this class all along, create a controller that's a neural net. So the pi controller, just like a neural net controller that we've been using, could take the current state, and it's going to calculate the u, or the action. And the idea here is that it's going to approximate pi. Pi is a function. Neural nets can represent functions. But we have the same old learning issue, is we don't have target outputs for optimal actions. In the block diagram, I haven't drawn it yet, we'll do that in a minute, is that we plug in a state, we get an action. We don't know what the action, whether it's good or not, until the action goes into the system and comes out the other side of the system. But as we'll learn a couple lectures ahead, is that there's a process called Q-learning that allows us to learn this pi function, or a way to figure out what the pi function is. And what's different here is that with Q-learning, we don't generate target outputs for the controller or for the pi function. We learn optimal actions to the targets using the rewards. One of the downsides to this whole thing is that you have to explore the entire state space and try all possible actions, because it's trial and error in some sense. You start out somewhere in the room, you move, you move, you move, and then you see whether you got out the door or not. And you have to try that from all possible starting points in the room, and you have to try all possible actions. That becomes difficult, and so Q-learning is a way to explore through the space that helps optimize that process. The upside is this works even with only partially observable states. Like if you have a robot and you have a limited number of sensors on board, it may not know everything about where it is in the environment, but it may have some limited information. All right, so here's the task that we're trying to do. And here's a block diagram that I've drawn to make this look like a control system. So the current state goes through the controller, which is the policy pi, and it generates an action. The action and the current state go into the system delta, and we get a new state. Also, looking at the action and the state, the reward function is going to give us a reward for taking that one step. And down below, as I've described that, the agent is in state ST. The controller chooses an action. So the policy pi chooses an action based just on the state. And then the environment responds with two things. First, a new state. That's the delta function. And a reward for taking that action from that state. Note the reward is based on the initial state where it started at the time t and the action taken. This thing does not look at the next state that it ends up in. It simply gets a reward for the motion or the action that it took. So one more thing we need to define is we're going to define a v function based on a policy. Earlier we said, well, v was equal to, scroll back up here, we'll find it. V is this string of rewards. Well, implied in here is that there is a policy that tells it, well, how did we go from state 1 to state 0 to state 1 to state 2 to state 3? So we'll explicitly define V as based on a policy. So if we have a policy pi already figured out, optimal or not, V superscript pi means we follow that policy starting at state st, and then we collect rewards as we go along. So once we tie V to a policy, then we can work our way forward to R0, R1, R2, R3 and calculate V. So definition officially, we start at state st, V is a function of st, and we follow the policy pi that's up here in the superscript. So what that means is that V pi of st, start at state st, move forward according to the policy pi, you collect a local reward, and then you keep moving forward step by step and collecting rewards following the policy pi. You can see now why we have to explore a lot of space, because you have to try all different policies pi and collect the rewards and see, well, which one gives us the most reward. Remember, V is the total discounted reward of following this policy. It's the sum of gamma to the I. This is a way to express it as a sum. So you collect all the rewards into the future and figure out, well, do you like that policy or not? So in terms of the equations, you start at st, pi gives an action, the action goes into the reward, and the state goes in, and we collect our reward rt, and we get our new state here. And then we do it again. We're at a new state, pi gives us a new action, we get a new rt plus 1 and an st plus 2. And the idea behind the learning or whatever process we're going to use is that we want the agent to find an optimal policy, and we're going to indicate that with a star. So any old policy is pi, an optimal policy has a star on it, and that is going to maximize V for each and every starting state S. Meaning no matter where we start in our room, if we follow pi star, we get to the door the fastest. So mathematically, you represent this as argmax of V pi of S. For all S, it just says in equation form what we set up here. For every S state in the room, we try a policy pi and calculate the V. And then we try another policy pi, evaluate the V, try another policy, and we keep doing that over all policies pi. And that's what the argmax says, is that it's not finding the maximum V, it's finding the maximum argument of the function. So it gives us the pi star that gives the max V for every single starting state in the room or the world or the environment. So to wrap up, V superscript pi is the reward when we start at S and follow a policy pi. And V pi star, or short notation just V star, is going to be maximum because pi star is the optimal policy, so it gives us the max possible discounted reward starting at S. So if you use pi star and you start anywhere in the room, you're going to get the most discounted reward. So that's what this says here. Pi star gives the maximum reward no matter what state S you start in. Okay, we're going to stop here. The next lecture is going to be an example where we look at this grid world where we have a goal and some policies and some local rewards. Notice that we have a reward here going into the goal, but that's going to happen next time.